Welcome folks, and in today's video we're going to look at the very important physics concept of conservation of momentum. And it's a concept in physics that's used to explain the strength of the motion of systems over time. And it is a tenet that's used to explain interactions from the very large celestial collisions right the way down to subatomic crashes. And I'm going to use our good friend Pac-Man to introduce this concept, and then we'll practice some problems. Okay, so Pac-Man gobbles up ghosts in straight lines, and that's quite useful because that means that this motion is in 1D, one dimension. Now, perhaps the game developers had other concerns at the time, but what should Pac-Man's motion be like? If Pac-Man is moving, gobbling up a ghost here, what I'd like to know is what would the motion be like after taking on board the lucky ghost or the unlucky ghost? The other question I'd like you to think about is what would the motion be like of Pac-Man, the system of Pac-Man and the ghosts, if Pac-Man swallowed two ghosts, this one and this one? So maybe stop the video and have a think about that. So our understanding of physics is based on this concept that that momentum before a collision is equal to the momentum after collision, provided there's no external forces and it's not an open system, if you like. And so we can set up a situation like this by looking at the momentum before and the momentum after. Now, the momentum before this collision is just a combination of Pac-Man's momentum, which is m times v, and also the momentum of the ghost. And the ghost was at rest. We're going to say the ghost was at rest. So that one is pretty straightforward. And then the momentum after is the total system. So now we would need to account for the fact that they're traveling together. And so if we look at these momentums, we can multiply the two momentum values together. And we're going to get 50 kilogram meters per second. Momentum doesn't have its own fancy unit, but there you go. And that would be equal to the combination of masses. So it would be the mass of the Pac-Man plus the mass of the ghost times the velocity. So provided you know something about the masses in that situation, you can get it. Now, let's say the mass of the ghost was 2 kilograms. So in that case, we could simply say that the velocity after, and sometimes it's called velocity prime, is equal to 50 kg meters per second divided by the combination of masses. So 5 kilograms plus 7 kilograms. And so you'll see that for Pac-Man, the velocity that Pac-Man is traveling after is not 10 meters per second, but something less. So if you like, the heavier system after this system right here would be moving with a velocity that's less than Pac-Man was moving with at the beginning. Another example that we might want to look at, what if Pac-Man had closed his gob and was like a pool ball and was moving to the right? And what if the ghost over here was moving to the left? And what if they happened to be moving with the same velocity and collided at this point? So what would happen in that case? What would happen in terms of their motion? Now the kilograms here is 5 and this was 2, remember. So maybe stop the video and have a think about that. So this is where vectors are very, very important. We would, of course, define one way as positive and one way as negative, so always a good idea to get into that habit. And let's just take some sample values and say they were traveling at 10 meters per second. Well, then the velocity vector here would be for Pac-Man would be positive, and so it would be 5 multiplied by 10. And so we would get 50 kilograms meters per second. Now, it is important to say at this point that for the ghost, it would be 2 multiplied by negative 10 because they're traveling in the opposite direction. And that would give us negative 20. So you already know conceptually, hopefully before, that there is, if you like, an overall vector that's moving to the right. So overall, there's a momentum of 30 kilogram meter per second to the right. So that would need to be maintained after the collision. And so what's going to happen is these good folk here are going to move off, and probably because this one is lighter, they're going to move off. This one's going to bounce more, but they are going to move to the right after the collision. The final type of scenario that you'll see in these one-dimension conservation of momentum is, what if there was an explosion, and let's say that Pac-Man has the ghost in her mouth, and let's say just for some reason just exploded, and the ghost of Pac-Man came flying out this way. Well, remember that in this case, always, if this system is considered a closed system, that the momentum before is equal to the momentum after. And so the momentum of the system before, we have to say in this case, because there was no movement, because the velocities are zero before, it would be 0 kilogram meter per second. And I'm going to have to make that one a little bit smaller. And so we've got to make sure that the momentum after is also equal to that. And so if the ghost flies off in that direction, then what we should see is that Pac-Man flies off in this direction. Now, the momentum is conserved, but the velocities might be different. So there is that factor of mass to take into consideration. So we're just going to look at a single example here that I've taken from earlier. A classic physics example, and we got some spectators as well there, Raccoon Mario. There's a cart on the left which is heavier and is at rest, and the cart from the right is going to hit the cart on the left with a velocity, and they're going to stick together. Now watch the motion after the collision. So hopefully you can see that the velocity after the collision was much reduced. And that's because of that extra mass of the system now. But it has to be said that the actual momentum before and after, the total momentums, should be equal. So what we have in front of us here is a typical type of problem. An astronaut of mass 80 kilograms throws a tool bag away from her with a speed of 2 meters per second. What velocity will she start to move at? Well, why would she be doing that anyway? Well, maybe there's a spaceship, the mothership, that she wants to get back to here. And maybe she has no other way of getting back but to use fantastic knowledge of physics. And she's stuck out in space, so there's less friction involved, and it would be a way perhaps to get moving to the left. So when we set this one up, of course, we say that the momentum before is equal to the momentum after. And the momentum before is the momentum of the astronaut and the momentum of the bag. And again, if we look at this, this is a scenario where there's no velocity, or the velocity is zero. And so we say that this is actually 0 kilogram meters per second. Now the velocity after, we know that there is some momentums, and it's the momentum of the astronaut and the momentum of the bag. And this symbol that I'm putting here beside momentum is called prime, and that generally means after. So always try to set these up as before the collision and after the collision. So when we do this, we're going to have the mass of the astronaut times the velocity of the astronaut prime, and the mass of the bag times the velocity of the bag prime. Now, we should also say that the mass usually in these scenarios isn't going to change. And so the mass of the astronaut here is going to be 80 kilograms multiplied by the velocity, which we don't know, the velocity after the collision. That's what we're trying to find out. We know that the mass is going to be 10 kilograms. And we know that this is going to be 2 meters per second. So we do know that. So we know that we have all of this from the other side is equal to 0 from before. And so now just a little bit of algebraic diggery-pokery would give us VA prime is equal to negative 20 over 80. And so what we're going to get there is a negative, and that's okay. Because what that means is if the bag was moving to the right and right was positive, then the astronaut's going to move with this velocity to the left, and that would have to be negative because in the opposite direction. In front of us we have another example here. On this example we might want to set, so we've got a person catching a ball, and it appears as though the ball is moving to the right. Okay, so the ball is going to come in here, it's moving with a velocity, and it's going to be caught. Now, because there is very little, so there is no momentum on the person at the beginning, we have to put in 0 there. But we know that there is going to be momentum because of the ball, because the ball actually has a mass and a velocity. So 2.50 multiplied by 7.50. So it does actually have a momentum. And we also know that that momentum is to the left. Now, it might be a good idea, because you know the momentum is to the left and that's going to be conserved, just to set to the left as positive, just to keep things nice and easy. Now, when we multiply the two of those together, we're going to get a value here of 18.75. So this is our momentum before. We know that that must be conserved, and so the momentum after is equal to that. Now we also know that the momentum after, they're moving together, so we're going to have to account for that and say that it's the mass of the person plus the mass of the ball, and they're going to move together with a velocity after, which is what we're trying to find. So we can also say that these masses is 72.5 kilograms, and that's times V. So we now have an easier one to solve from there, and so we can find out what the velocity of the system is after. Now 0.26 meters per second is reasonable. Always ask yourself at the end, is that reasonable? And that's a positive because it moves to the left and we set left as positive. But also it is reasonable because the ball was moving with a decent velocity, but it's quite small. And so when added to the mass of the individual here, that would be a reading that's good. So hopefully you found this video useful in terms of an introduction to conservation of momentum in one dimension. If you liked the video, just give us a wee thumbs up and hit that subscribe button.